So yesterday, I finished computer vision and Kaggle competition almost close to 100%. And today I started working on NLP, Natural Language Processing for TensorFlow. And in this Zero to Mastery course, he has taken a very simple data set. It's important to get end-to-end pipeline and understand it, and then we can work on a more complicated problem. So I think that logic makes sense. So going into the code, you can find that code here in NLP, and inside NLP there is simple NLP notebook. I might change the name later, but let's understand NLP and how it is different. This okay. Let's understand NLP and how that standard code is different compared to computer vision, which we did yesterday. So everything remains the same. Okay. We have to read the data set. Okay. Now, but in images, the images naturally internally are numbers. Brighter the spot, brighter the color, higher the number. And we can see 256 shades of a single color, and we can see three primary colors RGB. So 256 into 256 into 256 turns out to be around 8 to 10 million colors we can see. But whereas in text, we do not know how our brain understands words. Okay, we don't know how our brain processes and converts it into meaning, but for sake of deep learning, we convert it into a numerical vector, and then we convert it into a numerical vector which contains the meaning of the word as well. So first is vectorization without meaning, and then next is including the meaning in the vector. So we are embedding the vector with the meaning. So these two stages are extra. In vision, we had image as is. Here we have that extra step. So we take the data set. So let me just clear these inputs and read the data set. We take the data set and we pass it through these two stages, okay, for vectorization. So the stage is this: we specify maximum vocabulary size. So for example, whatever language you speak well, right, you will have around 5 to 10,000 or 15,000 words everyone approximately knows of a fluent language. So we specify that maximum vocabulary. Then we also specify the length of how long a general sentence is. We map one word to one number. It doesn't have any meaning. It's just random mapping, not random, but certain kind of mapping. And what is the sequence of such numbers we want? That is what this length is about. So we build a vectorization layer from Keras, okay, and we specify these arguments to it. That's it. So this one extra step is where we take the text we have, convert it into its vocabulary by calling this function adapt. This is what TensorFlow has decided. We just have to remember it. Okay. So what it does, it converts it to into these things. So for example, if I include a sentence which contains just one single word, the output, which is going to contain 15 numbers, here because it only contains one word and that word is going to be mapped to one thing, you see apparently entire is mapped to thing 7, text is mapped to 4, goes is mapped to 6, and here is mapped to 5. And when I combine them together, you see it is 7465, which is also 7465 here. And then something else is added extra, which is the word build. So you see one word mapped to one number as long as the length of this is same as the vector length we have specified. So this is the extra stage. So what we do here is, if this is what we are going to do, we take our data and we specify vocabulary of 50,000. Okay, 15,000 is the vocabulary generally for a fluent language. Let's include 50,000, right? Why not? And the vector here, the problem we are working on is tweet data. 140 characters. 140 characters, then it is going to come out to be maybe 20 or 40 words at most. So that's why I've chosen it to be 50 and I specify the vectorization. And whatever entire training data we have from taken from Twitter, we specify that to map the words into its numbers. And after we do that, okay, so after we do this mapping thing, we can actually check what the vocabulary is. So you see, I have also printed the length of the vocabulary, and apparently, even though I specified 50,000 words, this does not have those many. So upper limit of vocab here is 21,089. Pretty cool, right? One interesting thing, it has something called as UNK. UNK stands for unknown. If this layer comes up with a word which it does not know, then it is added into this. This is the unknown thing. That's why we have the token. And everything else, this is in the descending order of frequency. So here you can find A and the are most frequent words in English. It's common sense, right? So we easily find those are what are highest here at the beginning. And if we take a look at the tail end of things, we will find that these are the least frequent elements of this. So pretty good. Okay, so this is how we do vectorization. And after vectorization, this is simple dumb vector. A word is mapped to a number, a simple dumb vector mapping. Here we have specified 50 to be size, and for vectorization, I have given it two sentences. This is a dumb vector which does not contain meaning. So what would be the next step? Include meaning into this vector. We want to embed the meaning into the vector. And we have, that is what we have here. So one word is mapped to a vector, entire vector, which contains its meaning as well. And we'll specify the dimensions, depending on however complicated we want to specify. I'm specifying 64, good enough, I guess. So we have vector in which we are going to embed the meaning. Its dimensions I have specified as 64. And then this is the layer which actually embeds the meaning inside this vector. So this embedding the meaning inside, so we take the dumb vector, whatever we want, and we convert it into embedding. And when we see its output here is now not like we had here, in which we had just number and rest were zero. No, because it also tries to understand good morning means, it's most likely a greeting. Two people are there and we are saying hello world. Hello world might be a common word programmers use, so it might have context of a programming tutorial. So there are a lot of things. With just these four words there is a lot of meaning associated. If I say apple, I mean, it might be good apple, bad apple, so many things possible, right? Or it could be apple company. So the meaning is very complicated, and this tries to encapsulate into for in 64 dimensions. So this sentence is converted into 50 numbers, one vector of 50 numbers. For each number, it has converted into a 64 dimension thing. So this is the meaning. Okay, so embedding and these two are extra steps. So if you go to the model, like computer vision, you have input layer, final layer as output layer, and then in between you have hidden layer. So because it is text, we have vectorize and embed the meaning also after input. So we take the text, convert it into numerical vector, then we embed the meaning. So this, the vector in which we have embedded the meaning is called as embedding. Okay. And then we have a hidden layer. So we write the model as we did in a standardized way for computer vision because it is easier to debug. We want to check what is the shape at each and every instances. I have to just specify this run eagerly as true. I had not known this yesterday. So when I specify this and if I say, breakpoint here, I can actually debug this. And while the model is training, we can actually check step by step what is happening, what is the shape, whatever I want to check, we can just go through this. So this makes the whole debugging thing very easier, and that's why we do it. So we do this, we have taken this extremely simple configuration of model, and we still get accuracy of 57% ish. Computer vision, because images are very dense, one image is around 10 MB, and whereas in 10 MB you get 10 textbooks, more than 900 pages of text data. So images are a lot compute intensive, text is easy. Text is also easy to collect. So NLP has an advantage, but vision has an advantage because we can see the image. We can also understand what is happening behind the scenes of the neural network. So pros and cons of each. NLP is faster, but vision is easier to understand and experiment with. So this is the model architecture which gives you good enough accuracy, and then done. If you want to add even higher depth, so I'm gonna add another hidden layer here and add 10 100 neurons. So here it gives me accuracy immediately, very high accuracy of 88 90%. But if you check accuracy on the data which the model hasn't seen, that accuracy doesn't change much. So you see, this model is becoming very good at pretending to know the answers, but in actually when we test it in real life, its score is bad only. So this model, the one we had above, seems to be good enough. We are getting 78% accuracy only. So seems a good pipeline, end-to-end pipeline, starting from vectorize, embedding, and then internal layer and model architectures. This is end-to-end NLP pipeline. So I have done this. What is remaining is taking this and converting it into four, five, I think six, seven different types of architectures and checking which one is better and why. But step one is having this standard pipeline, and now you also do. So let's check and experiment with the rest of the models tomorrow.